What's up guys, and welcome to this tutorial on the 2018 final exam. We are going to go over question 5, which has to do with conservation of momentum and impulse and that kind of stuff. Okay, so let's get straight into the question. So it says students are performing an experiment in the lab. A 0.9 kilogram trolley is traveling at a constant velocity. Okay, so traveling at a constant velocity of 2.4 meters per second along a frictionless track. When a metal cylinder of mass m is dropped vertically onto the trolley with the metal cylinder continues to move with velocity v as shown in the diagram. Okay, cool stuff. Then it says the students use video analysis and they've plotted the displacement time graph or position time graph, which is shown. Okay, so question, let's see, 5.1.1 says use the graph to determine the magnitude of the velocity v of the trolley after the, okay, so after, so essentially here is before and anything after this point is after. Okay, how do we know this? Because the velocity is our slope or our gradient. So initially it's traveling at a higher velocity and then it travels at a lower velocity. Okay, so our velocity v is equal to our gradient, which is equal to our change in x, or change in y over change in x. In this case, we're going to use, let's use 0.1 here and 0.2 here. So our change in y is going to be 10,2 minus 4,8 over the change in x is going to be 0.1 is 5 minus 2. And if we plug that into a calculator, we get our velocity is equal to 1,8 meters per second. Okay, and it wants the magnitude, so we don't really care about the direction. Okay, and we get 3 marks. So 5.1.2. The law of conservation of momentum is a consequence of which Newton's laws? Okay, so that would be Newton's third law. That's just a theory question. Okay, and we get 2 marks from that. Okay, question 5.1.3. Says calculate the mass m of the metal cylinder. Okay, so for this question, we are going to use the conservation of momentum. Okay, so conservation of momentum says that the momentum before the collision is equal to the momentum after the collision, and we care about the momentum in the horizontal direction. Okay, so let's see. So we're going to say the mass of the trolley, velocity of the trolley, all before plus the mass of the, cylinder, velocity of the cylinder is equal to the mass total times the velocity of the total system, because they're traveling together at the end. Okay, so we know the mass of the trolley is 0,9 kilograms, the velocity is 2.4, plus we know that the velocity of the cylinder in the horizontal direction is 0. Okay, so this entire term goes to 0, so and that is equal to the mass of the trolley, which is 0,9, plus the mass of the cylinder times the velocity at the end, which we calculate as 1,8 meters per second. And so if we look at this equation, the only unknown is the mass of the cylinder, and so we can calculate the mass of the cylinder is equal to 0,3 kilograms. Okay, and we get 4 marks for that. Then we say, why is the vertical velocity of the falling metasphere not taken into consideration? Okay, so we already answered that in the previous question essentially, but if we want to give a formal answer, we can say that the momentum is a vector, and the velocity of the cylinder has no vertical component. Okay, but like I said, we pretty much answered that in the previous question. Okay, cool stuff. And that question is done as well. We'll get ourselves 2 marks. Okay, question 5.2. Okay, so a steel hammer with a mass of 600 kilograms is used to drive an iron beam into the ground. Okay, so the steel hammer falls a distance of 3.5 meters from rest under gravity before coming into contact with the beam. The beam is driven a distance of that, let's get that into meters, into the ground before coming to rest. Okay, ignore air resistance. Cool stuff. So we've got a nice diagram of what's happening as well. Okay, so question 5.2.1 is a definition. And okay, so the definition of conservation of mechanical energy is in the absence of air resistance or any external forces, the mechanical energy of an object is conserved. Okay, again, just a definition, and we get 2 marks right there. 5.2.2 says calculate the magnitude of the velocity of the steel hammer as it strikes the iron beam. Okay, so we just spoke about conservation of mechanical energy, so let's use that principle. Okay, so the mechanical energy before is going to be equal to the mechanical energy after. Okay, so what is the mechanical energy before? So we have mgh, let's use initial and final rather. Initial and final, mgh plus half, so that's the potential energy plus the kinetic energy, which is half mv squared. Initial is equal to mgh final plus, so that's the potential energy, plus half mv final squared, which is the kinetic energy. Okay, so at the top we know it has a mass of 600. Gravity is 9.81 or 9.8, just keep it there, times a height of 3.5. The velocity, it says it starts from rest, so this term goes to 0. Okay, at the bottom we can say that the height is 0, because we're taking our datum point as being this, because that distance is the 3.5. So let's call that our datum point. So at our datum point is the final, so that goes to 0. And so we have a half times our mass, 600, times our velocity squared, final squared. Okay, and the only unknown is v, so we can solve for v, and the velocity is equal to 8.28 meters per second. Okay, again it asks for the magnitude, so we don't care about a direction, but if we did care about a direction, it would be down. Okay, then it says 5.2.3 is a definition, state the work energy theorem. Okay, so we can say, I'm not going to write this out, but basically the work done by a net force on an object is equal to the change in kinetic energy of the object. So basically work net, what we get from the definition is that work net equals change in EK, which is also equal, and our work net is F net change in S is equal, change in displacement is equal to our change in EK. Basically, that is what we get out of that. Okay, so 5.2.4. Calculate the magnitude of the average net force the beam exerts on the hammer while the hammer is brought to rest. Okay, so how are we going to do this? So we just spoke about the work energy theorem, so let's go with that. Okay, So F net change in S is equal to change in EK. Okay, so F net is what we're looking for. The change in S is going to be that distance right there, which we said is 0.16 meters, is equal to our change in EK. Okay, so it's going to be EK final minus EK initial. Okay, so our EK final, it comes to rest, so it's going to be 0 minus, okay, a half times our mass, which is 600, times our velocity final squared. So our velocity we calculated as 8,28 squared. Okay, if you look at this equation, the only unknown is F net, so we can solve for F net is equal to minus 128,547 newtons. Okay, but what does this minus sign indicate? That's just a direction, so F net is equal to 128,554 newtons. Okay, we took down as being positive, so the net force is acting upwards, and that makes sense. Why does that make sense? Because our beam is going downwards, so the net force must act upwards to stop it. Okay. This should be enough space actually. So 5.2.5. The machine that is used to raise the hammer so that it can be used again has a power of 180 watts. Calculate the time the machine will take to lift the hammer through a height. So basically calculate how long it'll take to lift that hammer up. Okay, so let's see, what is the equation we're going to use? The governing equation is going to be power is equal to work over time. Okay, and what work are we trying to do? We're trying to lift this hammer upwards. So the work is going to be power is equal to mgh over t. Okay, so we know the power is 180 is equal to the mass of 600, 9,8 times the height of, we want to lift it 3.5 meters, all over the time. Okay, the only unknown here is time, so solving this equation we get t is equal to 114,33 seconds. Okay, and that is our final answer, and we get 4 marks for that. Okay, cool stuff, and that's that question. So that question was quite long, I guess, 27 marks, but yeah. Okay, and in the next video, we will do question 6. Okay, thanks for watching, guys.